So let's talk a little bit about quantum physics. So this is going to be some weird stuff. Now, the first sign that there was a need for this new kind of thing called quantum physics, first sign was in something called black body radiation. So I've talked about this before, but as a quick review, we know that everything glows, gives off radiation at every single wavelength, and we can make this into a graph. So we have the kind of the intensity, the amount of radiation you get out of something glowing versus wavelength of that glowing thing. And everything has a characteristic shape of intensity of light that it gives off at every wavelength, depending on its temperature. And we see characteristic shapes that might look like this for something that's a little warmer. Then as we go a little bit colder, so as we go kind of into the red, we get slightly different shapes. But these general shapes are called black bodies. And what they noticed was the black body radiation that they saw looked something like this. So physicists were doing experiments and they noticed this is what we see. And then they had some theories and some equations to predict what they were observing. But the predictions, the observations, didn't match with these predictions. Their theories looked like this. So if we put some scales onto these kind of rough graphs, we've got very small wavelengths, so these are short wavelengths, and we have long wavelengths on the right-hand side. So these small wavelengths are moving towards the ultraviolet range of the spectrum, and what we noticed was theory was predicting that energy in the ultraviolet was exploding. It was going up to infinity. Infinite energy as you go to the ultraviolet. This became known as something called the UV catastrophe. So in science, our real purpose of science is to explain nature. And right here, we can see a deficiency in our theory, a problem with our theory. Theoretically, we're predicting that a black body should increase to infinite energy as we go to the ultraviolet. Observationally, we see that the energy goes up, reaches some peak, and then comes right back down. So what we had to do was make this theory match with this observation. So we had to kind of bring this theory down in line, and we had to bring this cutoff down so that it would gradually end up decreasing as we went to smaller and smaller wavelengths. So to fix this, to make this correct, to fix the ultraviolet catastrophe, there was a physicist by the name of Planck. Max Planck. And Max Planck was really, really good at math. He was more of a mathematician than anything else. And what he did is I'm just going to do the math. I'm going to figure out what math I need to get the observations, to make the theory match the observations. So Max Planck figured out, what do I have to do to make this theoretical graph that explodes match with this graph that doesn't match with what we observed. So this is what we call an empirical derivation. He's kind of figuring out, what do I need the theory to be to make it match my observation. So he did some math and figured out that the energy inside of an atom that's glowing to give off this radiation has to be equal to n plus 1/2 times h times f, where n is just an integer from 0 to 1 to 2 to 3, all the way up to whatever number you want. H is a constant, and this is where the math really came in, figuring out what this constant was. 6.626 times 10 to the negative 34 joules times seconds. And we gave this a name. We named it after the guy that figured it out, Planck. So this is Planck's constant. And then F is the frequency of the light that is making this black body curve. So we figured out this equation. Now where this really becomes more applicable and where we're starting to see where we would start to eventually see some matching up was in the field of atomic and molecular line emission and absorption spectroscopy. So quantum physics, which is more or less just the study of the super, super small things, figuring out how atoms kind of work, really started with determining this black body radiation equation, the energy inside of an atom to make this theoretical curve match with this observed curve, all developed by Max Planck. So we're going to take this information, take this data, and we're going to expand with it. We're going to start to figure more things out. So quantum physics kept growing, and we started figuring out more kinds of ideas and more explanations, basically governing behind how light works. The second big observation after this, solving this ultraviolet catastrophe, is something called the photoelectric effect. And the photoelectric effect was how light ejects electrons from a material. And we're going to see a picture of what this looks like. So, the photoelectric effect. We can set up a circuit. So I'm going to draw a little circuit. I'm going to hook up to a battery. And then I'm going to complete the circuit over here. But what I'm going to do is I'm going to put a little plate on one end. And then another plate on the other end of this circuit. And in between this, all this area right here is empty space. So I turn on this battery and I'm trying to get electrons, current to flow. And nothing's going to happen. Because again, there's empty space right here. So then what I'm going to do is I'm going to try to encourage some things to flow by giving some energy to this plate. To this plate right here. I'm going to try to give it some energy. So I have electrons that are flowing around. Electrons are going to build up on this plate, on this kind of curved plate. And I'm going to try to convince them to jump. So I'm going to shine some red light in. And nothing's going to happen. So instead of just giving up, I'm going to shine even more red light in. So I'm going to send in another beam of red light. And nothing happens. And I'm going to take that red light, and I'm going to take these red light beams, and I'm going to make them really, really big and intense. And still, nothing happens. So what I'm trying to do is give the energy of this red light to these electrons and convince them to jump. But nothing happens. And then what we noticed happened is I could shine in just a little bit of blue light. And as soon as I shine in a little bit of blue light, one of these electrons will suck up that blue light and it'll jump. And I'll get current flowing. I could shine in a piece of green light. Nothing happens. A slightly stronger piece of green light, and then I might get an electron jumping. So what I notice here in this photoelectric effect is red light shining on my little curved plate. I get nothing. No matter how much intensity I shine. Green light, I notice, if I shine a lot, then I can get maybe electrons jumping. So we'll put electrons jump, maybe. If I shine in blue light, and it doesn't have to be a lot, then I get electrons jumping. So this was a mystery, this photoelectric effect. Why was red light not working, and why was blue light actually working? Einstein came up with a solution for this. Same guy that came up with relativity came up with the answer for the photoelectric effect. Einstein said, we're going to assume light is made of particles. And let's call these particles photons. And each of these photons has some energy. And that energy is equal to h times the frequency. So this should look familiar. This was the same as Planck's equation, basically, for describing the UV catastrophe. Except here, Einstein is assuming that light is just a single particle. And furthermore, Einstein said, not only is light particles, he also said individual photons, individual pieces of light energy. Hit single electrons and eject. But only if the photon has enough energy. So since he's a physicist, he of course loves equations, and we come up with an equation that describes this. We have this equation, Ke, and I'm going to put a little electron down here, is equal to HF minus Be. So Ke, with this little electron, this is the electron energy. So that is the energy of these tiny little electrons that are jumping. So they have some energy as they jump across, as they move. HF is the energy of the photon. So that's the energy of the incoming light. That's the energy of this little piece right here, this little piece of incoming light coming in. And then Be is something called the binding energy. And the binding energy becomes the key in all of this. The binding energy is how tightly your electrons are stuck to this curved plate. So here we can see why we get this result of red doing nothing, green doing a little bit, and blue doing things very easily. So red light has the smallest energy. So in this equation down here, the energy of the light, this HF, this red energy, if it's small, as is the case with red light, then that energy isn't enough to overcome this binding energy. So if I do a small number minus a large amount of binding energy, I'm going to get a negative number, and I'm going to have no kinetic energy for photoelectrons to make them jump. Blue light, however, has a lot of energy. So this HF for blue light is higher than the binding energy for the metal, how tightly glued the electrons are to the metal, and these kinetic energy electrons, they can get enough energy that they can jump across this gap. So this was Einstein's explanation for the photoelectric effect. This actually won Einstein the Nobel Prize. So everything about relativity that we still use today didn't win Einstein anything. He won for the photoelectric effect. So let's keep talking a little bit about this concept of light having energy. And in particular, let's talk about photons. And photons are particularly strange, which made them a big mystery for quantum physicists. The strange thing about photons is that they can behave like waves, which we've seen in the double slit experiment, or they can behave like particles, which we see in the photoelectric effect. So if photons sometimes behave like waves and sometimes behave like particles, that means that they're both. A photon is both a wave and a particle. So we have different equations that we use to describe these. To describe these photons. We have the momentum of a photon is equal to h over lambda, where h is Planck's constant and lambda is the wavelength. So this would be the kind of the wave nature of light. We also know that E is equal to hf. Energy of light is h times the frequency of that light, which is also equal to h times the speed of light divided by the wavelength. So this is a way that we can calculate the energy of light. So you have an equation for momentum, an equation for energy, and we can note that we're kind of ignoring the relativistic additions to these equations. Those just come in the form of Lorentz factors of gammas. And then finally, we have the wavelength of light. It's just a reshuffling of this momentum equation, where lambda equals h over p. And we're calculating wavelength in this way, using Planck's constant divided by a momentum. This is getting something called the de Broglie wavelength. And this lets us calculate the wavelength, kind of the wave characteristics of things that we normally think of as being particles. And actually, this de Broglie wavelength allows us to describe any type of matter as waves. So I can describe the wave characteristics of something like an electron as a de Broglie wavelength by using Planck's constant divided by the momentum of that electron. So that's kind of a discussion of light. It leads us into this theory and this concept of quantum physics. And then we get to the really crazy stuff, something called the Heisenberg-Uncertainty Principle. So Heisenberg is pretty popular in popular culture. He's in a TV show called Breaking Bad, if you've ever seen that show. That's how the character got his kind of code name. Comes from this Heisenberg guy that came up with the uncertainty principle. And this is kind of a wacky theory that turns out to be true. So we have this guy named de Broglie. And de Broglie kind of starts to say, hey, you can describe everything as a wave. Which is a little bit weird, right? Electrons are tiny little particles. How can they be waves? Well, de Broglie said, it's true. You can describe this thing as a wave. Now, when we think about it, a wave is actually just a probability. And the real purpose of a wave is to make a probabilistic interpretation of where a wave is. Okay, so a wave is a probability prediction of a particle's characteristics. And we have something called a wave function. So we use the Greek letter phi to represent something called the wave function. Sorry, that's the Greek letter psi. Represents the wave function. And the wave function predicts where a wave is. So it's a natural extension of de Broglie's theory of describing everything as waves. Now, instead of just describing it as a wave, we're describing it as a wave function, which is a probability that predicts where a wave is going to be. It's a kind of very statistical mathematical representation. And what we have in quantum physics is the science of the very small. And that's where all this light theory, describing the UV catastrophe, the photoelectric effect, and this de Broglie wavelength idea leads us to this world of quantum physics, which is the science of super small. And when you go so small, you kind of lose exactness. You lose precision. There are lots of reasons for this, but this means that we describe quantum physics in terms of usually probabilities. and something we've worked with in physics in your labs, probabilities and uncertainties. So quantum physics is an inherently uncertain kind of field. We're quantifying these uncertainties. And what Heisenberg did is he quantified uncertainty in position and uncertainty in momentum. And he did this in an equation. Because again, physicists, we love our equations. The Heisenberg uncertainty principle tells us delta x times delta p has to be greater than or equal to h divided by 4 pi. And what are all these variables? So the delta x is kind of like your position wave. It's your position uncertainty. It's how accurately you know your position. And delta p is your momentum uncertainty. And what this tells us is that there's always uncertainty. So if I knew my position perfectly, I would get a 0. If I knew my momentum perfectly as well, I would also get a 0. And when I multiply those together, 0 times 0 gives me 0. This breaks the Heisenberg uncertainty principle, which says that I have to get greater than or equal to h over 4 pi. So what that tells us, what this equation says, is you cannot always know both position and momentum. Okay? There is always some inherent uncertainty. That's a fundamental result of the Heisenberg uncertainty principle.